Let's go ahead and start now. So today we're going to finish off chapter 4. We'll talk about cyclopentane briefly. We'll spend most of our time today talking about cyclohexane, our most important cycloalkane. At the end, we'll talk a little bit about fused rings, where we have cycloalkanes fused together, and cholesterol is a great example of fused rings. And then if we have a couple of minutes left over at the end, we'll just talk a little bit about the exam. So this figure here shows some conformations of cyclopentane. We can see the planar conformation, and the planar conformation of cyclopentane has 108 degree bond angles, very, very close to 109.5, close enough that there is no angle strain in the planar conformation of cyclopentane. But the planar conformation of cyclopentane is quite high in energy. What kind of strain do we have in this conformation? Not steric strain, torsional strain. We have eclipsing interactions. The carbon-hydrogen bonds are all eclipsed with each other, so we have a large amount of torsional strain in the planar conformation of cyclopentane. So that conformation is high in energy. To relieve that torsional strain, you'll have either one atom twist out of the plane, and you get a conformation called the envelope. I don't know why they call it an envelope. I don't really see a resemblance between it and an envelope. Or we can have two carbons twist out of the plane. Usually one ends up above and one ends up below, and we end up with something that's called a half chair. Okay, that's something that makes a little more sense, as we'll see later on. So these are the low energy conformations of cyclopentane, the envelope and the half chair. They're lower in energy than the planar conformation because they have relieved torsional strain by twisting one or two of the 5 atoms in cyclopentane out of the plane of the others. Okay, any questions? Okay, so let's talk about cyclohexane. Cyclohexane is going to be our most important and most interesting cycloalkane. Cyclohexane is special because it can adopt a conformation, a type of puckered conformations. These two conformations we would call puckered because they're not planar. And cyclohexane has a puckered conformation that it can adopt, in which it is free, completely free of torsional strain. So what I've drawn for you here on the board is a Newman projection looking down 2 of the parallel carbon-carbon bonds in cyclohexane. So in our 6-membered ring, we have bonds on opposite sides of the ring that are parallel to each other, the 2 that I'm holding here in my hands. And so if we were to make a Newman projection down those 2 bonds, we would see that all of the groups coming off of the carbons involved in those bonds are staggered. Okay? That's what we've drawn right here. And that's what I have here in my hands. Perfectly staggered, so totally free of torsional strain. No torsional strain in this particular puckered conformation of cyclohexane. And it doesn't matter which 2 bonds you choose. I could choose these 2. We see the same thing. Perfectly staggered. I could choose the final 2, and we see the same thing. Perfectly staggered. Okay? So it doesn't matter how you look at this puckered conformation of cyclohexane, it is perfectly staggered, so it's free of torsional strain. The bond angles are 111 degrees. That's close enough to 109.5 that it is also free of angle strain. Okay? So this particular conformation is referred to as the chair conformation. So if I hold it sideways like this, and we have these 4 carbons in a plane, this carbon above the plane, and this carbon below the plane, you can see it kind of looks like a lounge chair where this might be the headrest, and down here this would be the footrest. So personally, I think that name makes a lot more sense than envelope. This one is half of a chair because half of the ring looks like it's in a chair shape and the other half is more planar. Okay? So this is what the chair looks like. We have a model, a ball and stick model from the book that also shows you the chair. And there's some vocabulary here that we need to learn with the chair, and that is axial and equatorial. Okay? So we have hydrogens. The hydrogens labeled in blue are referred to as axial hydrogens. The carbon-hydrogen bonds are all parallel to each other. And if we were to make an imaginary plane that cut through, there was an imaginary plane that was roughly parallel to our cyclohexane. This chair is not planar, but we would see that the axial hydrogens would be perpendicular to that imaginary plane. Okay, so they're referred to as axial. And then the ones in white are referred to as equatorial. They're around the equator of our chair conformation. So it's important for us to be able to draw chair conformations. This is not an art class, and I am probably the world's worst artist. That's not one of my talents. But it is important for us in organic chemistry to be able to draw certain structures very clearly so that others can understand our drawings. And chair conformations of cyclohexane are one of those things. So you should practice drawing chair conformations until you're comfortable being able to draw them well. I'm a terrible artist. I can draw them, so if I can do it, you can do it. I have had about 30 years of practice, so I do have that advantage, I guess. But here goes. Let's draw a chair conformation. Okay. So here is a chair conformation. And on this one, we're going to draw axial hydrogens. Okay. These axial hydrogens all parallel to each other. Okay. So this is a chair, and we've drawn the axial hydrogens in on that chair. And we could draw the equatorial hydrogens in as well on the same chair, but let's draw a different one just so that it's not as cluttered and it's easier to see them. Okay. That didn't look very good. Okay. I'll draw my equatorial hydrogens in. Okay. All right, so let's go over some hints and tips for how to draw cyclohexanes chair conformations clearly. Each chair is comprised of 3 sets of parallel lines. I showed that to you on the model that we have 3 sets of parallel carbon-carbon bonds. So to draw a chair conformation clearly, we have to do the same. We have to draw 3 sets of parallel lines. So if we take a look, this line is parallel to that line. This line is parallel to that line. This line is parallel to that line. Okay, 3 sets of parallel lines. So you can check yourself when you draw your own chair conformations to make sure that you have 3 sets of parallel lines. Okay. And then the axial hydrogens, straight up or straight down. Okay, question?
Just on the official definition of axial versus equatorial, axial is like 90 degrees of the plane that the carbon.
Yes, perpendicular. That carbon-hydrogen bond is perpendicular to the pseudo-plane, I guess you could say, of the molecule.
Okay.
So then how do we draw the equatorial hydrogens, the equatorial carbon-hydrogen bonds? The equatorial carbon-hydrogen bonds should be parallel to 2 of the carbon-carbon bonds and parallel to 1 other carbon-hydrogen bond. So let's take a look and see if we've done that. This carbon-hydrogen bond It's parallel to that one, and they're both parallel to these carbon-carbon bonds, okay? This carbon-hydrogen bond is parallel to these two, and also parallel to this carbon-hydrogen bond, okay? And then this carbon-hydrogen bond, parallel to these two, parallel to that carbon-hydrogen bond, okay? I might have missed this one. This one and this one are parallel, and they're parallel to this and that, okay? So each equatorial bond parallel to two bonds in the ring and one other equatorial bond, okay? So we have a whole bunch of parallel lines if we've drawn it correctly. Any questions? Now, it's important to draw these chair conformations correctly, not because it's an art class, as I mentioned, but because you need to be able to make structural drawings that can be clearly interpreted. And so if you follow this pattern, your audience will be myself and the TAs when we're grading your exam. We will be able to clearly interpret what you've drawn. If we can't clearly interpret what you've drawn, then it's very, very difficult for us to give you credit on problems, okay? So we know that in cycloalkanes, we do not have full rotation. We have restricted rotation about the carbon-carbon bonds in a cycloalkane. But we know that we can interconvert between different conformations. We have, with cyclopentane, the ability to interconvert between the envelope and the half chair. And in cyclohexane, we have the ability to interconvert between two different chair conformations. And that process is known as ring flipping. And when we perform ring flipping, what happens is the equatorial and the axial hydrogens exchange with each other. So in the model that I'm holding for you now, we have purple bonds representing the equatorial carbon-hydrogen bonds. I apologize if you're colorblind, but that was the only way to do this. Purple bonds representing equatorial, and we have blue bonds representing axial carbon-hydrogen bonds. So we can perform a ring flipping process and do this, and now all of a sudden the purple groups are axial and the blue groups are equatorial, okay? We can flip it back, okay? This is not a magic trick, and this is not something that's only relevant to models. This is relevant in nature because if we have a bottle of cyclohexane, the molecules in that bottle are rapidly interconverting between the two different chair conformations of cyclohexane, and that is referred to as ring flipping, okay? So we need to understand how ring flipping occurs. And we have a figure that shows this. This is different from how it is explained in your book. I mentioned before, this is my favorite organic chemistry textbook. I think it's an excellent book for many reasons. But it does have its flaws. There's no such thing as a perfect textbook. And the main flaw of this textbook is there are some topics where, in an attempt to simplify things, it goes too far, oversimplifies, and actually introduces errors, okay? And the ring flipping of cyclohexane is one of those cases. So we'll explain the process, and then I'll explain how it's a little different from what is in the book, okay? So what we have here is we have a chair. Okay, this is a chair conformation, one of the two chair conformations. And this diagram is similar to the ones we showed you on Wednesday for the rotation about carbon-carbon bonds in ethane and butane. So we have energy on the y-axis. We don't have a dihedral angle on the x-axis. We're just moving. It's just time moving from one chair to the other. So what's going to happen initially is we're going to take, the way I've oriented my chair, we've got 4 carbons in the same plane, and then we've got one above and one below. So one of the carbons that's not in the plane is going to rotate to be in the plane. And that's referred to as a half chair. Unfortunately, it's the same name as the low energy conformation in cyclopentane. But you can see why this would be called a half chair. If this is a full chair, we take away the footrest, now we have half of a chair, okay? The half chair is an energy maximum on this pathway from one chair to another. Why would the half chair be high in energy? What kind of strain do we have here? Yeah, we have a lot of torsional strain. We have 5 carbons in the same plane. So we have a lot of eclipsing carbon-hydrogen bonds. Okay, so we have a lot of torsional strain. So one problem with this figure is it has kilojoules instead of the kilocalories we prefer. 45 kilojoules per mole is 10.8 kilocalories per mole. So we've said that there's 20 kilocalories per mole available at room temperature. So it's very easy for a chair conformation to undergo this kind of twisting and access the half chair conformation at room temperature. Okay, not a problem. But this is high in energy, so it's not going to stay here. This carbon will continue rotating up. And then if you read the book says you form something called a boat. Right? This kind of looks like a boat. You've got the 2 ends of your boat, maybe like a canoe or something, or a rowboat. But the boat is high in energy. What's the problem with the boat? I'm going to hold the boat like this. Tell me what kind of strain we have in the boat. Okay, there's more than one correct answer. I heard steric hindrance. That's correct. We have these 2 hydrogens pointing towards each other. We have steric hindrance. If you make a Newman projection down the bonds I'm holding, you'll see we have torsional strain too, because we have eclipsing carbon-carbon bonds here, or carbon-hydrogen bonds. So torsional strain, as well as steric strain. The boat is fairly high in energy. It's actually not as high as the half chair, but it is pretty high. So what happens, instead of generating the boat, as this carbon comes up, the molecule twists. You can see as it twists, we're relieving the torsional strain. Right? We're no longer eclipsing. We've twisted to avoid the eclipsing. We've also relieved the steric strain because these hydrogens aren't as close together when we twist. So the twisted version of the boat can be called the twist boat. Some books call it a twist boat. The book that I got this figure from called it a skew boat. It's skewed. That basically means the same thing as twisted. So the thing you need to correct from the book is that when you are converting from one chair to another, you don't form the boat. The boat is not on that low energy pathway, but the skew boat or the twist boat is instead. Okay, so that's the correction. And if you make the model, you can see why the skew boat is lower in energy than the boat, because we've relieved both steric strain and torsional strain. Okay, question?
Where was the torsional strain again?
Torsional strain in the boat?
On the side there.
Right here, yes.
Got it, okay.
Okay. All right, so once we get to the skew boat or the twist boat, now we take our other carbon, we rotate it down so that it's in the plane with the 4 other carbons. We access our second half chair intermediate, and then we keep going, and that gives us our other chair. Okay, so we have 5 species that we encounter on this pathway. We have the chair, the one half chair, a skew boat, a second half chair, and then finally the other chair that we are accessing. Question?
When does it untwist from the skew boat? Does it just untwist when it goes back to that chair?
Yes. As it's so what happens is you have a local energy minimum. The skew boat is a local energy minimum, and then you have to go back uphill from that local energy minimum. So as you're twisting it, it's going higher in energy, but then there's a payoff once you get over the top and you get down to the low energy chair. So I told you that this difference in energy is 10.8, right, readily accessible at room temperature. This energy difference is 5.5 kcals per mole. So the skew boat, 5.5 kcals per mole higher in energy than the chair. And then the boat, which is accessible, the boat is accessible at room temperature, but it's not on that low energy pathway. So here's a model of a boat from your book showing you the torsional strain here, showing you the steric strain here. The boat is about 7 kilocalories per mole higher in energy than the chair. Okay, so higher in energy than the skew boat, but still accessible at room temperature, but it is not on the pathway between the two chairs. Okay. Any questions about ring flipping? So I would suggest practicing this and recognizing the identity of the species at we have the minimum, that's the chair. We have the maximum, that's the half chair. And then the skew boat you would refer to as a local minimum. Okay? Any questions? Yes? No, it is not. That is a good question. The half chair actually has more torsional strain than the boat does. So the boat is 7, the half chair is 10.8. Question. Right. So if you were to draw the path to the boat, it would be a different path. I'm not sure. It might go through the half chair, but it would break off somewhere up here and not go down to the skew boat. Okay, so it would be an entire, so that's what I mean when I say the boat is not on the pathway. You twist the lowest energy pathway from chair to chair does not access the boat. The boat is straying off the path. It's another branch. Okay? Other questions? All right, so you might wonder, what's the deal? What's so interesting about ring flipping? We're just interchanging the positions of hydrogens. Right? And that really isn't too exciting in my opinion, just interchanging positions of hydrogens. But when we put a substituent on our cyclohexane ring, now it becomes more interesting. Okay? So this yellow ball here is a substituent. We can just call it a methyl group for now. So we have methyl cyclohexane, and we have one chair conformation where that methyl group is equatorial. And then we flip to the other chair, and now the methyl group is axial. So when we have a monosubstituted cyclohexane, the position of that group will exchange from axial to equatorial or vice versa as we perform ring flipping. Are these two chairs equivalent in energy or different in energy? Different. Which one is lower in energy? Okay, having the group equatorial, the substituent equatorial will be lower in energy than having the group axial. Why? Steric hindrance, excellent, or steric strain, right? So if there's a difference in energy, that's usually due to a type of strain. If we have our substituent axial, it is too close to the axial hydrogens, and so we have steric strain. Note that we do not have torsional strain. We don't have torsional strain in any of our chair conformations, right? We showed that right here, and I showed you with the model that we have a perfectly staggered arrangement of bonds. So we're never seeing torsional strain in a chair conformation. We saw it in those intermediates, right? Torsional strain in the half chair, but not in the chair itself. So what we're introducing is steric strain by putting our substituent in the axial position. And we refer to that type of steric strain as a 1,3 diaxial interaction. Okay? I showed it to you on the model. We can show it to you here on this figure that has ball and stick models. I don't like the way they extended this out just so that you could actually see this in 2 dimensions okay. This bond is no longer than any other bond in that, any other carbon-carbon bond in that molecule. But what you see is that when you have a substituent such as a methyl group axial, now it gets too close. As you rotate about this carbon-carbon bond, these hydrogens get too close to those axial hydrogens, and that introduces the steric strain. And we don't have that steric strain when we have the methyl group equatorial. Okay? So this is where ring flipping becomes important and interesting when we have a monosubstituted cyclohexane. So let's draw the ring flipping process. I've shown you the model. We've looked at it on the board. We also have to be able to draw it. So we'll draw one of our chairs of methyl cyclohexane. And we don't have to draw the hydrogen in when we're drawing cyclohexanes. We can just draw the substituents, but I strongly recommend drawing the hydrogens on carbons that bear substituents, and I'll explain why in a moment. It makes it much easier for us to see what you're actually drawing, okay? So we do a ring flip, and the easiest way to do ring flipping when you're drawing cyclohexanes, drawing chairs, is you have this. I usually like to draw the one with the vertex on the left pointing down and the vertex on the right pointing up. That's just the way I like to draw them. But then when I flip it, the vertex on the left is up and the vertex on the right is down. That's the easiest way to show that. And so here is the ring flipped version where we have our methyl group axial. And if we wanted to, we could adjust the length of our equilibrium arrows to show that this particular equilibrium between these chairs is going to favor the one on the left with the methyl group equatorial. Question, Claire? You could draw it on any carbon because it doesn't matter. The same as when we talked about nomenclature, you don't need a number for methyl cyclohexane. You could pick any carbon in the ring to do it. But usually if you have one substituent, it's easiest to put that substituent either here or here. And then it's just going to flip. If it's here, it's going to flip up to here. If it's here, it's going to flip down to there. But I caution you, as I draw this, there's a caution that I have to give you, which is when you're drawing two different chairs of the same molecule, the up and down relationship of the substituents must remain the same. What I mean by that is that this carbon, we would say the hydrogen is pointing up and the methyl group is pointing down. That cannot change. If all we're doing is ring flipping, the up-down relationship of those groups cannot change. We look here on this chair on the right, hydrogen up, methyl group down, the same as what we have over here. So the up-down relationship never changes. It's only axial and equatorial that change as we go from one chair to another. Questions? All right, so there's a way to relate. So at equilibrium, we can use spectroscopy to measure the ratio between these two chairs, because they do interconvert with each other, so there's an equilibrium. And at equilibrium, we would have 95% of the equatorial methyl chair and 5% of the axial methyl chair. And there's a way to translate that ratio into the difference in energy between those two chairs. And this figure here, which is not in your book, but as I mentioned, they're all available on Learning Suite, shows us that relationship. And that uses this equation that you learned in general chemistry, delta G naught equals negative RT ln K. This class is almost exclusively qualitative. We're not going to be plugging numbers into this equation, but we're using it as a way of taking a ratio at equilibrium and converting that into a difference in energy between the reactant and the product. So this is a very simple equilibrium. We have one reactant and one product. So the K is just going to be the concentration of the product divided by the concentration of the reactant. So we look up here in this table, we see methyl group, we see 595. That's the ratio I gave you. That would give you a K of 19, and you plug 19 into this equation and pick the right constants at room temperature, you end up with a difference in energy of 1.7 kcals per mole. Okay? And that difference in energy is often referred to as an A value. This particular table doesn't show you that term, but if you see the term A value, that is just the difference in energy between having a group in the equatorial position on a cyclohexane versus the axial position on a cyclohexane. Okay? And we can measure these ratios. We can determine them by spectroscopy. And so that allows us to convert that into differences in energy. What we can see from this table is that those ratios and those differences in energy between the two chairs depends on the size of the group. The larger the group, the more energetically costly the 1,3 diaxial interactions are, the bigger the difference in energy and the less of the axial chair we will have. So you see here fluorine. Fluorine is our smallest atom other than hydrogen that we will see attached to a carbon. And so the difference is not very big, 60-40. That gives us about 1/4 of a kcal per mole. Okay? Isopropyl, a little bit bigger than methyl. We see a 97-3 ratio. That translates to 2.1 kcals per mole. Tert-butyl, on the other hand, is so big that we cannot detect it in the axial position. Using spectroscopy, we have yet to detect the tert-butyl group in the axial position. We can use molecular modeling programs to calculate the energy differences between having the tert-butyl group axial versus equatorial. And we find 5.5 kcals per mole, which tells us that we would have less than 0.01% of that. So now we can see why we aren't able to detect that. It's such a small number. So for purposes of the class, we will assume that tert-butyl groups are too large to be axial, and we're only going to have them in the equatorial position, and we won't see the ring flipping when we have a tert-butyl group on a cyclohexane. Okay? Any questions on the relationship between equilibrium ratio and energy? Yes, please, Grace. That's an amazing question because that is related to our next topic. So you led right into our next topic that we're going to talk about. And that is having two groups on a cyclohexane. So di-substituted cyclohexanes. And we are going to answer your question. Before we do, there's one thing we need to do. So we'll have to wait about 5 or 10 minutes before we answer your specific question. But let's draw di-substituted cyclohexane. Okay. Okay. So this is 1,4-dimethyl cyclohexane. And we're just drawing the skeletal version. We're not drawing a chair. And so we're using wedges and dashes to show whether those methyl groups are pointing up or pointing down, pointing out of the board or pointing back into the board. Okay? I'm going to draw 2 of these. Okay? All right, so I told you the name of this compound on the left, 1,4-dimethyl cyclohexane. If you've read the reading for today, you know there's something else in there. But based on what we've learned from nomenclature up until now, you would call this 1,4-dimethyl cyclohexane. What would we call the compound on the right? The same thing. We cannot have one IUPAC name for 2 different compounds. Are these 2 different compounds? They are indeed. They're not the same. So something is amiss. We'll correct it in a moment. But we have to learn a new term, stereoisomers. Okay? These are not the same compound, but they have the same molecular formula, so they have to be isomers of each other. But the atoms are connected together in the same way, so they're not constitutional isomers. We have a 1,4 relationship between our substituents. They're both methyl groups. That means the atoms are connected together in the same way. So stereoisomers are isomers that differ only in the orientation of atoms in space, or 3-dimensional space. Okay? So the only difference between these 2 compounds is that the one on the left has the two methyl groups pointing up on the top face of the ring. The one on the right has the methyl group, one methyl group pointing up and one methyl group pointing down. So those are stereoisomers, a new category of isomers. We have two now, constitutional isomers, stereoisomers. So we need a way to distinguish between them in IUPAC nomenclature, and that is two new prefixes. The prefix cis. Cis refers to having those two groups on the same side of the ring. And then we have trans. Trans refers to having our two substituents on opposite sides of the ring. One up, one down. So we simply put this prefix in front of the numbers, and that's our IUPAC name. This is cis 1,4-dimethylcyclohexane and trans 1,4-dimethylcyclohexane. Any questions on the numbering or on the naming? Yes? You are also leading into the next topic, which relates to her question. So which would be lower in energy? We're going to answer that question by examining the chair conformations, but do you have another question first? It goes in front, and then you would put a dash. I'll just go ahead and put the dash here. So you would put cis or trans in front of the numbers with a dash. Yes? Up or down. So up or down always stays the same. Equatorial or axial depends on which chair we are drawing. So let's look at the cis isomer first. We're going to answer your question, which one is more stable, but we have to look at the chair conformations. So the cis one, let's raise the board up just a tiny bit here. Okay, we'll draw that right here. Okay, so cis, I've got them both pointing up. We count 1, 2, 3, 4. Over here we have it pointing up. Okay. So this is one chair of cis 1,4-dimethylcyclohexane. Then we flip it. So this one goes from being up and equatorial to up and axial. This one is going to go from being up and axial to up and equatorial. Okay? All right, any difference in energy between these two chairs? No, same. So what we would have at equilibrium is a one-to-one mixture of those two chairs. They would just be a freely equilibrating 50-50 mixture of chairs. Okay? All right, now let's look at the two chair conformations of trans 1,4-dimethylcyclohexane. We'll draw those over here. Didn't make that very parallel. It's a little bit better. Okay, we'll draw this one up. And we count 1, 2, 3, 4. This one's going to be down. Okay. We do our, oh, I know what I did. I drew the left up first. So we'll draw this one now. Okay. So this is now going to be up equatorial. 1, 2, 3, 4. And this one is going to be down equatorial. Okay. So these are our two chair conformations for trans 1,4-dimethylcyclohexane. Are these equivalent, or is one lower in energy than the other? Okay, this one's lower. Why? Both groups are equatorial. How much lower in energy is this than that? You can go ahead and look at the screen and it'll tell you. How much does it cost us to have a methyl group axial? 1.7 kcals per mole times 2. So this would be 3.4 kcals per mole higher in energy than that. And that translates into roughly 99 to 1. That's somewhere between the isopropyl, which is 97.3, and the tert-butyl, which is all and nothing, basically. Okay? So we'd have roughly a 99 to 1 ratio of these two. So we could go ahead and adjust our arrow if we wanted to. Okay? So for trans 1,4-dimethylcyclohexane, this chair is lower in energy than that, which tells us that if we're going to compare trans to cis, which maybe was what your question was going to be, we only need to look at the low energy chair of the trans isomer because that's going to represent 99% of it at equilibrium. Okay, another question? Okay, that's a good question. It's still going to prefer the chair because it's free of torsional strain. So even though you've introduced some steric strain, it still prefers the chair because that's better. You can't get rid of the steric strain completely to rotate. You're going to relieve some of it, but at the cost of additional torsional strain. Good question. All right, so let's now compare the trans isomer to the cis isomer. Which one's lower in energy? Okay, let's hear a loud enough answer for me to hear. Trans, exactly. All we have to do is compare the low energy conformation of the trans, and both of these are the same, and we see that this is going to be 1.7 kcals per mole lower in energy than either of these, and so the trans isomer is more stable than the cis. Any questions? All right, what happens when we get 3 substituents on a ring? I'll let you answer that yourselves in the context of this iClicker question. Let's get out our iClickers. And we have one compound, a tri-substituted cyclohexane drawn for you. How many different chair conformations will this compound have? 2. There's no more than 2 chair conformations for any given compound. Okay? And you have 5 choices here, all right? So that should tell you something as to how you would approach this iClicker question and decide which of the following is the most stable, lowest energy chair conformation of this molecule. For your reference, there are A values given on the side here. So let's go ahead and talk to each other and answer the question. This group always converses very quietly. It's okay to talk louder. Okay, as I look at the answers, I'm starting to see the results of the discussion, so it's good. Keep it going. It'll take about maybe 20 to 30 more seconds to come up with our final answers. So there's two popular answers, and obviously one is right and one is wrong. So all right, so just a couple more seconds here. Any more answers? Going once, going twice. That looks like everybody. Okay. So, step one, which of the two chairs of these five choices, or which two of the chairs out of these five choices represent this compound? B and C, exactly. All three groups have to be pointing up, and they have to have a 1, 2, 4 relationship. If you start at the bromine, you count 1, 2, 4. So you have to have a 1, 2, 4 relationship, and they all have to be pointing up. Over here, we've got a 1, 2, 3 relationship. Same here, so we can throw those two out right away. And then over here with A, it's 1, 2, 4, but we've got up, up, down. Okay, so A is not this compound. If I had asked you which of the chairs here is the lowest in energy, the answer would be A, right? Because all three of the groups are equatorial. But we didn't ask you that. We asked you which of the following is the most stable chair of this compound. So A is not that compound, so that's not the correct answer. So out of B and C, which one is the lowest energy chair of the compound we drew? B. Why? Who would like to raise their hand and explain why? Okay, Minnie? Okay, so we have the largest substituent equatorial. We also have 2 equatorial and 1 axial. And it's the smallest substituent that's axial. And then when we flip it, we end up with 2 axial, 1 equatorial. And if you want to, you can add these A values up, and you find, right here, we're only paying 0.38 kcals per mole of energy to have that bromine axial. Here we're paying a much larger price, about 4 point something kcals per mole to have the methyl and the isopropyl axial. Okay? Any questions about how to analyze a problem of this nature? Okay, last thing we'll talk about today is fused ring systems. Fused ring systems are where you have 2 or more cycloalkanes fused together, meaning that they share 2 carbons and 1 carbon-carbon bond. So here we have 2 6-membered rings fused together. They share these 2 carbons, and they also share the carbon-carbon bond connecting those 2 carbons. You can have transfused rings or cis-fused rings. The ones we'll focus on now are the transfused, meaning that the 2 hydrogens at the points of fusion are trans to each other. When you have a transfused ring system, you cannot perform ring flipping. It is impossible. It's hard to explain why it's impossible, but if you make a model of this, you can make a model of this molecule. It's called transdecalan. And if you try to do the ring flipping, your model will break. If your model breaks when you try to do ring flipping, that's a sign that that's not going to happen in nature. Okay? So this molecule is locked in position with no ring flipping. It's very, very rigid. So on our next slide, we have, not that one, we're skipping that. We have a model of cholesterol here. Okay? So this ring system shown on the left is called the steroid ring system. When we have 4 rings, 3 6-membered rings and a 5-membered ring fused together in this way with a little bit of a kink, that is a steroid. You've presumably all heard of steroids. We'll talk about them throughout the entire course because they're steroids that do all kinds of things in our bodies, both good and bad. But they all have this fused tetracyclic ring system. And here's cholesterol over here on the right. Cholesterol is a steroid. And you see you have a double bond here, so it's not cis or trans, but you see here we've got the trans ring fusion. Here we've got the trans ring fusion. So there's no ring flipping in cholesterol. So cholesterol is an extremely rigid molecule. Very flat, very rigid. Is cholesterol soluble in water? No. We've got one OH group, 27 carbons. Definitely not soluble in water. Okay? And that's a problem because as cholesterol, it has to be transported through the body because it's not soluble. So we have these lipoproteins that can encapsulate cholesterol and transport it through the bloodstream to the places we need it. And if it leaks out of those proteins or those proteins aggregate, then we get plaques in our arteries and veins. So cholesterol, the fact that it is nonpolar and rigid, tells us what it's used for, right? You probably associate it with bad, you probably have a bad connotation when you hear the word cholesterol, but the truth is cholesterol is essential. The average adult has 200 grams of cholesterol in his or her body. And what cholesterol does is it rigidifies our cell membranes. So the lipid bilayer, on its own, the lipid bilayer is extremely fluid. Those tails are constantly moving about, rotating, and so you have a very, very fluid membrane. For our cell membranes to work properly, they have to have a certain degree of rigidity. And that rigidity comes from cholesterol molecules. Cholesterol molecules can insert into the cell membrane. This figure here shows that nicely. We've got cholesterol molecules inserted in here. We do have that OH group that can hang out at the top. But then we have a very, very rigid molecule next to these flexible and fluid molecules, and we get the right amount of rigidity in our cell membranes by having the right amount of cholesterol in our bodies. Okay, so this is another example of how the structure of a molecule enables it to perform a certain function, and that rigidity of cholesterol is due to the transfusion in the ring systems. Any questions? All right, we'll stop there. Good luck on the exam. I'll just tell you, take your molecular models to the exam, but take them in a clear plastic bag so they can be inspected. And if you're ready to take the exam today, don't be afraid, go take it. Usually the highest average comes from students who take it on the first day, usually goes down from there. So, and if you're wanting to stay safe from COVID, you have to wear your mask the whole time in the testing center, so it's probably the safest place you can be on a Friday night. So good luck, and we'll see you on Monday.